Welcome back to New Findings of the Universe. Today, we will talk about this topic that bends the mind without breaking the facts. Black holes are not objects in the ordinary sense. They are regions where space-time is curved so extremely that the rules you and I rely on for everyday intuition just stop working. When people picture a black sphere, what they are really seeing is the boundary called the event horizon. The point of no return for light and for anything else that tries to climb back out. Inside that boundary, our best classical descriptions of space and time lose their footing. Outside it, the black hole still leaves fingerprints everywhere. It pulls on orbits. It drags space-time when it spins. It heats matter into X-ray bright whirlpools, and it even sculpts the color and geometry of the light that barely escapes. Let's start from a simple, useful image. Imagine a heavy ball pressed into a flexible sheet. The sheet sinks, and marbles rolling nearby curve inward. That picture is not the whole story, yet it captures the essence. Mass and energy tell space-time how to curve. Curved space-time tells matter and light how to move. A black hole is the most intense version of that conversation. And strangely, the hole itself is likely smaller than you think. The true engine sits deep inside as a singularity in the simplest models, a place where density shoots to an absurd extreme and where our equations throw up their hands. Whether nature really builds an actual singularity is an open question, but we know this: the horizon behaves as a real border in the outside universe. There are many sizes of black holes. The stellar kind are born from the death of massive stars. The giants live in the centers of galaxies and weigh millions to billions of times the mass of the Sun. Between those extremes might lurk the intermediate clan, which are harder to pin down, but increasingly hinted at by observations. The point is not the precise category. The point is that the same underlying physics runs the show across the board. Curvature, gravity, radiation from the stuff falling in, and a surprising amount of order hiding inside the chaos. If you and I camp outside a black hole and watch a rock fall in, what do we see? First, the rock moves inward and seems to slow as it approaches the horizon. Then it appears to freeze just above the boundary, growing dimmer, redder, and finally fading into darkness. From our vantage point, we never watch it actually cross the horizon. That is not an illusion of cameras. It is the direct result of time dilation and gravitational redshift predicted by general relativity. The closer you are to strong gravity, the slower your clock runs relative to mine far away. The light from the falling rock has to climb out of a deeper and deeper pit. In doing so, it loses energy. Its color slides toward the red and then beyond the visible. And its signal weakens until it is gone to our eyes. From the rock's own perspective, the story is very different. Its local clock ticks normally. There is no flashing sign that says event horizon ahead. Passing the horizon does not feel like hitting a wall. It feels like crossing an invisible line in the sand. The real wall is deeper in, where the classical description breaks down. That contrast to descriptions of the same journey that cannot be reconciled by common sense alone is a perfect example of why black holes are intellectually addictive. They force us to accept that time is not universal. That light is not just light, but a messenger that pays a toll to gravity, and that what you can know depends on where you stand. Add spin, and the plot thickens. A rotating black hole drags space-time around with it, a phenomenon called frame dragging. There is a region outside the horizon, the ergosphere, where space-time is pulled so hard that everything, even you, even a beam of light, is compelled to rotate in the direction of the spin. You can still escape the ergosphere if you have the right push, but you cannot stand still inside it. The very fabric beneath your feet is sliding. This sliding frame is not science fiction. We have measured frame dragging around Earth with gyroscopes in orbit. And in the environment of a black hole, the effect grows ferocious. Black holes do not shine on their own, but their neighborhoods can be spectacularly bright. gas spiraling inward forms an accretion disk. Friction, magnetic turbulence, and shocks heat that gas to millions of degrees, and hot gas glows in X-rays. If the central engine is a giant in a galactic core, the disk and its magnetic fields may collimate twin jets that punch out of the galaxy and radiate across the electromagnetic spectrum. Point a radio array at such a core, and you can trace those jets across intergalactic distances. Point an X-ray telescope, and you find a hard, flickering beacon whose brightness changes hint at the size of the inner disk and the spin of the whole. Then there are the rings themselves. With very long baseline interferometry linking dishes around the Earth, we can resolve the shadow of the horizon in nearby giants. The orange donut that gripped the world was the shadow cast on a glowing magnetized plasma, and the asymmetry in that ring carries information about rotation and orientation. That image required patience, clever algorithms, and the kind of global cooperation that astronomy is becoming famous for. It also delivered a new kind of ruler. By fitting models to that ring, we weigh the whole and test relativity under pressure, and we listen. When two compact objects spiral together and merge, they send out gravitational waves. Faint ripples in space-time that sweep past our detectors. Those waveforms encode the masses and spins, and the moment the horizons became one. Black holes, once purely mathematical creatures, now show up in multiple senses, in light that got heated by the fall, in radio maps of jets that carry energy away, in delicately reconstructed silhouettes, and in spacetime's own whisper as two wells fuse into one deeper well. Multiple messengers, one story, gravity and geometry running the table. Classical gravity says nothing escapes a horizon. Quantum field theory says the vacuum is not empty. It seethes with short-lived pairs that borrow energy from uncertainty and give it back quickly. Those two statements meet at a black hole's edge and produce a subtle, beautiful consequence. Stephen Hawking showed that when you treat quantum fields in curved spacetime, a distant observer will detect a faint thermal glow from the black hole, as if the horizon had a temperature. The details are technical, but the moral is crisp. Curvature and quantum fluctuations conspire so that some field modes that would have canceled no longer do. And the result is a small outward flow of energy. If energy comes out, the mass of the hole must go down by the same amount. Shrinkage speeds the glow, which speeds the shrinkage, and over enormous times, a lonely black hole evaporates. No one has directly caught this radiation from an astrophysical hole. It would be colder than the cosmic background for the massive holes we know today. But the logic of fields and curved backgrounds is a coherent framework used well beyond this one prediction. It also seeds a puzzle called the information problem. If a hole fades away into featureless heat, where did the detailed information about what fell in actually go? Our best instincts say it should not vanish. Our best semi-classical calculation seems to allow it. The tension is a sign that gravity and quantum theory have not yet been welded into one finished language. Meanwhile, laboratory analogs mimic the mathematics with sound waves and flowing media and report thermal effects at horizons that are sonic rather than gravitational. Those experiments are not proofs about the cosmos, but they are encouraging echoes. They tell us that the marriage between horizon physics and quantum fluctuations has legs. And they keep theorists honest about which parts of the argument are conceptual and which parts are just bookkeeping. Black holes sit at the junction where our two great theories need a referee. That is why even a whisper of quantum behavior on a horizon matters so much. A spinning black hole does more than rotate. It grips space-time and swirls it. Inside the ergosphere, that swirl is unavoidable. There is a clever thought experiment proposed by Roger Penrose that shows you can steal a slice of that rotational energy without crossing the horizon. Send an object into the ergosphere and have it split into two pieces. Arrange the split so that one piece falls into the hole on a trajectory that effectively has negative energy with respect to infinity, while the other escapes with more energy than you sent in. Conservation keeps the books balanced. The hole loses a pinch of its spin energy, and you pocket the difference. Real jets are not doing the clean version of this with tidy chunks, but magnetic fields threading a spinning hole can extract rotational energy on similar principles. The lesson is that horizons are not batteries. Yet the space-time around a rotating hole is packed with usable energy if you know how to couple to it. This is also where a common confusion shows up. People hear that space-time near a horizon can move faster than light and imagine a speed limit broken. The rule that nothing outruns light applies locally. It says that no particle can zip past a nearby beam and beat it in a short race run shoulder to shoulder. But frames of reference themselves can shear and slide relative to one another in ways that, from far away, look superluminal without violating that local rule. Cosmic expansion uses the same escape clause. Very distant galaxies recede from us faster than light because space between us grows, not because they are boosting through a fixed stage. So, a rotating black hole gives us an extreme, visceral example of how motion and energy are not only about rockets firing, they are about the stage itself moving. By learning to read the stage, the dragging, the horizons, the allowed and forbidden paths, we stop arguing with the script and start using it. That mindset shift is the real gift of this topic. Gravity is geometry, and geometry can do work. You would think that once matter is caught, it just drops straight in. In reality, most of it circles, collides, and circles again in a thin, hot disk for a long time. The reason is angular momentum. Anything with even a tiny sideways motion wants to conserve its spin as it moves inward. To drop closer, it must shed that spin. The shedding happens through friction, magnetic turbulence, and collisions that move angular momentum outward while allowing mass to drift inward. That outward transport of spin is why disks glow. Atoms get pummeled, electrons get shoved, and radiation pours off. Compared to the sun's gentle fusion, disks can turn mass into radiant energy with startling efficiency. No wonder the central engines of bright, active galaxies outshine their hosts. In some systems, magnetic fields grab charged particles and channel them into narrow, oppositely directed jets. Those jets can carry energy and momentum far out of the galaxy, light up in radio and X-rays, and sculpt the environment on intergalactic scales. The exact launch mechanism is still an active field of research. It likely mixes the disk's turmoil with the black hole's spin, braiding field lines, twisting them, and flinging plasma out along the poles. Whatever the microphysics, the macro picture is clear. Black holes do not merely swallow, they regulate. They heat their surroundings, they starve or feed star formation in their host galaxies, and they anchor feedback loops that shape cosmic structure. All of this has a counterintuitive side effect, because losing angular momentum is hard. Dropping all the way in is hard. Disks can persist for a very long time. Matter can circle a great many times, heating and radiating and colliding, before it finally surrenders the last sliver of spin and slips beneath the horizon. That is why the accretion environment is where we learn the most. It is slow enough and bright enough to study, yet close enough to the edge to reveal the rules. The glow is not from the hole, it is from the traffic jam at the toll booth. General relativity is generous. The same equations that describe a collapsing star also admit time-reversed cousins called white holes, where nothing can enter and everything can only exit. Those solutions are mathematically neat and physically slippery. We have no observational evidence for a white hole in our universe. Still, some quantum gravity ideas suggest that the end of a black hole's life might connect to a brief white hole-like release, a way to reconcile evaporation with information recovery. Whether that story survives better calculations is an open question. But it is the right class of question. What does spacetime do when curvature reaches its most extreme and quantum fluctuations cannot be ignored? Then there are wormholes, tunnels linking distant regions of spacetime. Stationary, traversable wormholes seem to demand exotic conditions that violate energy expectations. And every attempt to make them healthy within known physics runs into new obstacles. Yet even failed attempts teach us. They reveal what energy conditions must hold, what quantum inequalities forbid, and how causal structure fights to protect itself. The more we try to cheat the speed limit with geometry, the more we understand why the limit exists and where the loopholes truly are. Here is where I land after walking through all of this with you. Black holes are not only endings, they are laboratories. They test gravity where it is strongest. They invite quantum theory onto the same stage, and they hand astrophysics a set of engines that power some of the brightest beacons in the universe. They challenge common sense with time dilation and with horizons that split perspectives. They challenge technology by asking us to resolve something barely wider than a ring of light at the heart of a galaxy. And they challenge theory by daring us to make sense of evaporation, information, and the deep structure of spacetime. If you carry one idea away, let it be this. When gravity is geometry, the path to understanding is not to picture a familiar object that happens to be dark. It is to picture the stage changing shape, dragging everything with it, and letting quantum fields hum against that curve. Once you accept that point of view, the weirdness becomes a map. It tells you what to expect, what to measure, and where the next surprise is most likely to spring. And around black holes, surprises are not a bug. They are the feature that keeps the science honest and the wonder alive.